present you with the basic features of preCICE, and I'll present you how to get started with it by showing an example of a FSI problem. But I want to state that preCICE is not limited to FSI simulations, and also not limited to using OpenFOAM as fluid solver. Okay, I think after Alice's presentation, you have been familiar with FSI programs like the blood in the heart, or here we can see that there are already a lot of existing CFD methods to simulate a flow around a wingtip, and there are also a lot of finite element methods to simulate deformation and displacement of the wingtip. But what if we want to simulate both at the same time? Then we need some coupling methods to couple these two solvers together, which means that it's not I put the fluid solver and solid solver in one folder, then they can find each other and couple and communicate with each other. And this is a case that preCICE can be put into use. preCICE is designed with the basic idea that we want to reuse the existing CFD and FEM codes, which means that's why it is a library, which means we want to enable users to call the functions inside their solver instead of put their solvers under one framework and do a lot of changes. So it's designed to be a minimally intrusive library to do the coupling. And so this is like the idea. We want to couple between the CFD word and the FEM word, but now it's not only limited to this word, but this is the most use case, at least in China, I think. So here is a diagram of the basic features of preCICE, and I'll give a brief introduction about them. At first, it can do communication, and all these features presented here can be configured in one file. So it's not very complex. And for the communication, you can choose MPI ports and TCP sockets. MPI ports is fast in some cases, like 10 times faster in some cases, but most of the time we default to TCP sockets because it's robust for the normal OS systems, and the communication between the processes are fully parallel and peer-to-peer. Secondly, preCICE can do data mapping, which is this feature would be needed if you have unmatched meshes at two sides of the coupling surface, which means, for example, for the flow around the wing, you may want to have very fine mesh for the boundary layer in the fluid, and it's not necessary to use this fine mesh in the solid. And preCICE can do the data mapping, which is basically interpolation with different methods to communicate it by communicating the data. And this mapping could be said to be conservative or consistent, because for some quantities we want to keep it physically reasonable. And you can also have direct mesh size, which means we don't want data mapping. This feature is mainly used for it's not for surface coupling, but for volume coupling, because with preCICE you can also do volume coupling, like to do a multi-scale simulation, like you have a macro scale simulation, and in each finite element inside the macro field, you do one micro simulation. Then you only need one upscale or average quantity from the micro simulation. You don't need to map it actually. So there you want to use direct mesh access. And this mapping can be computed on any side of the mesh. And then the third part of the configuration would be the coupling schemes. With preCICE, we can do serial or parallel coupling, which means you can execute the participants, the different solvers, one after each other, or start them together, and after one at the end of the time window, we communicate data and we start together again until the end of the next time window. But for serial, it will do one by one, which is costs a little bit more time. And you can also choose explicit or implicit coupling. This is designed for by the explicit coupling, we mean that we do one iteration for each time window, and then we move to the next time window. We don't care what kind of results are there. But this is not recommended for strong coupling, because then you get send some totally unphysical values to each other, and the simulation will break. So we can also do, so then the implicit coupling is recommended. There we will restart the time window until this time window converges, and then we move to the next time window. And for the compositional and multi-coupling scheme, we want to say that we can support support a coupling of more than 2 participant solvers. And about equivalent and Atkin, I think if you have noticed this in Ali's presentation, it's mainly about we have some numerical methods designed here inside to help accelerate the convergence of the coupling problem, like quasi-Newton or Atkin under relaxation. And in the end, we have a new feature in the version 3, preCICE version 3, which is a time interpolation. And this is designed for the simulations which have the participants in which the participants have different time steps, different time step length at both sides. So for example, I have a blue participant A and with the time step 0.1, and the time window length is like 0.5 or 6. But for the participant B, I have a time length 0.25. It's already fine enough for this. And when the participant A is asking data at 0.1 from participant B, we do a waveform interpolation rather than the constant value or linear interpolation, and this gives better prediction for the coupling problem. So I think this is still too abstract here, but then I want to show you what people do with preCICE. Here I mainly show the FSI problems, and this is a simulation from the Hack. He simulates the fluid with OpenFOAM, and the solid is with calculix. And so he shows a membrane movement that is converted into energy. So it's actually the flow is actually the ocean flow. And then here we see a case that the particles hitting the elastic board, the elastic plate, and it can deform. And this is from the University of Luxembourg. The particles are simulated with XDEM, and the solid is also with, and the plate is also with calculix. And with this, it's basically the same as one Ali has shown before. It's a two-phase flow with interfoam and the elastic flap with calculix. So in this talk, I will first start with an example of coupling 2 toy Python solvers to show how to use the API course provided by preCICE directly. If you are a developer of the solver, you may be interested in this part. And in the second part, I show a FSI problem simulation, which is where we coupled fluid in OpenFOAM and solid in DO2 to show how to use an adapter, etc., and how to do the configuration. And this slice is published in GitHub if you want to have it. I'll also show the QR code in the end, so it's not if you are not in a hurry, you can also scan there. And some notes for this talk. At first, you are not expected to try things live because the installation takes some time and some concentration. So I don't think it's recommended here. But you are encouraged to ask questions live, and feel free to interrupt me. And all the software used here can be found in the demo virtual machine, which can be. I think there is an instruction through this link. You can find how to install it. And fourth, we want to stress that everything presented here is free software. preCICE is fully open source, and all the adapters, all the tutorials, all the websites are presented in this link. This is a link for our preCICE organization. So let's start with an example. We couple two toy Python solvers. So at first we want to see and to run this simulation, you will need to have preCICE version 3 and Python 3 and the common packages like NumPy and matplotlib. And you need the preCICE Python bindings because the solvers are written in Python, and we need some translation tools to make preCICE understand them. And at first, I'll show you what the two simple Python scripts do. So we have a generator and a propagator. The generator basically generates random data at this edge, and propagator is supposed to convect and diffuse this boundary data, which is supposed to be coupled, which is supposed to be sent from the generator into this 2D field. But the convection and diffusing equation is quite arbitrary. And this is a pure unidirectional coupling, which means that we send the boundary data of velocity from the generator to a propagator, and then we move to the next time step. We don't send anything from propagator and generator, and we also don't do any iteration to make it converge because there is no convergence program. And here is how the generator looks like. First, we have a 1D mesh, which is just a uniform mesh. And then we have a delta t, which is a time step length, and we start from t0, and the total runtime of this simulation would be 0.1. And in each time step, we want to generate some random values of velocity. And what propagator do is similar. First, we create a uniform 2D mesh, is 20 by 20, and then we have a time step length, which is the same as the one we have in generator. And then we give a boundary value at the red edge, which is initialized as the y coordinate of the mesh. And then the total runtime of the propagator is 0.2. And this is a arbitrary convection diffusion rule. And then we run this. Then we first run the generator Python file, and then we run the propagator file. Maybe you can notice here the file structure. We have a folder which contains the propagator and generator subfolder. In these two subfolders, we place the Python file. And from here, you can see that the simulation is totally uncoupled. The boundary value of the propagator is the y coordinate. And then, if you have installed preCICE and the Python bindings correctly, you should be able to import preCICE like this. Then we initialize a preCICE object. First, we want to tell the name of this participant, the solvers we call participant, and we want to tell where is the configuration file for this couple simulation. And the solver preCICE index and solver preCICE size is only used when you have multiple processes for one participant. And here we simply have one preCICE for this for the generator, and so the index is 0. After this, we construct the object, and with this object we can call different functions provided by preCICE. Then we define the coupling mesh, which is for the generator, the coupling mesh is the mesh itself. And to define the mesh, to tell this coupling mesh to preCICE, we need to use set mesh vertices. So here we get the coordinates of the mesh, and we tell the mesh name. Then you can get vertex IDs from preCICE. Yes, then we initialize participants. This initialize should be done after you have set the mesh and initialize the object. And then we want to advance the coupling because with preCICE, because if you have noticed before, the total runtime of the two participants are not the same, and this is not allowed by preCICE. So if you use preCICE to solve the coupling problem, we use preCICE to control when to stop the simulation. So that is what participant is coupling ongoing do. You use this to check if this participant should still continue to solve. And participant advance DT is just is to advance this simulation to delta t with the time step DT, and this time step is also decided together by preCICE and this solver itself. Yes, at first we want to get a maximum available time step size from preCICE too. The maximum time step size is like, for example, you have a time window size of 0.5, and you have 0.2 as a time step length as a time step length in participant A, and in the end you have 0.1 time step length, and there you can't use 0.2. You need to get maximum available time step size from the preCICE, which is 0.1, and you choose the minimum value between these two time step lengths. So we have set some things here. It's not completed, but let's just run it. And here you can see that if you we start the two participants in two terminals. And you can see that before you start the propagator, the generator will wait for the propagator to start. And then, yes, the simulation is ongoing. Okay. But you can see that the field is still uncoupled. It has a different color, but it's not a random boundary condition. It has a different color because different people are running it. So we have, because we missed something in the couple simulation, which is very important. That is to write and read data. And here is an example from the generator. And generator mesh need to write the velocity data to preCICE buffer, and propagator will read this data from it. So after we have set a mesh, we also tell this is to show how to use these preCICE API functions. And in the next example, I will show how to use OpenFOAM adapter. And then you need to tell preCICE which data you want to exchange. And then you read the data by giving the relevant information here. And after that, you advance. And you do similar things in the propagator. Of course, you need to read data before you advance. But after this, it should work now. I couldn't make a font larger because it's a video. Sorry. Now we can see that it's working. The propagator has received the random boundary values from the generator. And in this case, we use the most basic unidirectional serial explicit and nearest neighbor mapping configuration. But in the next example, we want to show something more complex. And because the configuration file in preCICE might be a little bit annoying if you have more participants and more data to exchange, we have a visualizer tool to visualize this config. And you can see here, you have a generator which sends the data to generate a mesh, and this data is sent to generate a mesh from is then mapped with the nearest neighbor method to propagator mesh, and this data is then sent into propagator to solve the simulation for the whole field. And here you can see what kind of coupling schemes and communication methods you have chosen. And with this visualizer, it's easier to spot the possible errors in your configuration. Okay, now let's move to the next example, how to use a preCICE configuration or the ecosystem. So at first, let's have a look what kind of solvers preCICE can couple. As I have shown in the toy program, we have our in-house solver, which is very simple, but you can do it if you want to use if you want to do some very basic coupling problem. Sometimes you only want to check if the couple is working, not just the real problem. But you can use different languages, and we provide bindings for different languages. And for the CFD solver, you can use the one you like, and most often used one is OpenFOAM. And for FEM solver, you can also use different available solvers, but they are all open source. And for particle solver, we have some tutorial. We have some examples use this, but I don't think we have adapters for them. So, as shown here, the solvers are connected to preCICE through an adapter. And now we want to know, what does the adapter do? Why do I need it? So this is the thing between the solver and preCICE. So for OpenFOAM, the adapter communicates with OpenFOAM through function object, and it communicates with preCICE through a chat library. And first, it can read and write data. For boundary values, we only take surface coupling into account here. And OpenFOAM will write the data into adapter, and the adapter can write the data into a preCICE buffer, and then to another participant. And secondly, it can redo iteration. This is needed for implicit coupling, because we need to do checkpointing and restart the iteration. And there we want to store some information before we start this iteration, because we still want to go back, and the adapter can help you do it. And then the time step size thing I've talked before. The time step size is not only decided by OpenFOAM, but preCICE will set a maximum limit to this time step size.
Sorry, where do you get the adapter?
It's also available in the preCICE GitHub link. I can show you the GitHub link later. There are a lot of information here. Okay, here. So this is a documentation page on our website, and it has instructions about how to install it, how to configure it, and how to extend it. The extend it is quite important because for OpenFOAM we have some we can communicate some values that we have with the depth itself. You can already communicate a lot of data, but if you have a very unique solver that you want to send some value like permeability to another participant, this is not possible because this is not a default value in preCICE in OpenFOAM. And then you can refer to this extending page and tell the adapter how to communicate this data, and it's very easy to do actually. Yes. So the example would be a channel flow. Inside we have a perpendicular flap, which is elastic. It's a very classic example. And this tutorial is available here. It's also in the tutorials page. To solve this problem, we provide already different solver combinations, as you see here, and they can be arbitrarily combined. And here are the results of the x displacement of the flap tip, which is a displacement here. And you can see that there are mainly two types of results from these combinations. Some are because of the different orders of FEM methods available in these solid solvers, and some are because we have incompressible fluid in OpenFOAM, and I think we have compressible fluid in Utils also. But most of them would match. And to run this tutorial, you will need to have preCICE version 3 and a recent OpenFOAM version. For example, the 2312. And you need to have the OpenFOAM preCICE adapter. And for the solid, I use DL2, so I also write DL2 and DL2 preCICE adapter here. And they are all available through this, reachable through these links. And the file structure of this case, of this coupling problem, looks like this. We have a configuration file at the most outer layer of the folder. And then we have a subfolder for the fluid participant, and we call it fluid OpenFOAM, and it has a normal OpenFOAM case structure. But here you can see that we have a preCICE dict, which is like also a configuration, but inside OpenFOAM to tell OpenFOAM what kind of information I need from you. And in solid DL2, we have the parameters PRM file to tell what kind of to configure the physical parameters of the flap, and also the information, communication to preCICE. And I didn't use the parameter from the tutorial directly, but I did some minor changes to demonstrate some features of preCICE. For example, in the configuration file, I reduced the maximum time because to spare some time, and I switched to a most basic serial explicit coupling scheme because I want to increase the difficulty of the coupling scheme step by step. And for the solid, I lower the solid density from 3000 to 42, which means that I have a stronger coupling between the two participants because the solid is much lighter. Then in the OpenFOAM, we need to do some configuration for the case, which is like we use moving or velocity for the coupling surface. And we use the displacement Laplacian solver for the dynamic mesh. I wouldn't explain this further because I think all of you know OpenFOAM better than me. And then we need to load the OpenFOAM adapter by adding the function object in control dict like this. Then we configure the adapter within this preCICE dict file in the system folder. First, we tell where is the configuration file, and what's the name of this participant, and which modules I use. This is a FSI program, so you can basically use FSI module, but if you want to use others, you can also read the documentation, choose the fluid or heat conduction, heat transfer, coupled heat transfer module, or write your own module. And then we tell OpenFOAM where is the interface, from where I want to gather data, what data I want. I want to read from you, and which data I want to write into you. And this is a parameter PRM file in the DO2 folder. We do similar things. We tell this is fixed tells DO2 which simulation I want to run because we have put that elsewhere, and we also tell the place of the configuration and participant name and mesh name and data I want to communicate. And this is a visualization of the config. You can see it more straightforward what information. So it's basically I sent the force from the fluid to solid and get a displacement backwards. And RBF thin place planes is the mapping method, which is based on radial. Sorry, I don't remember the full name. And then we have a look of the configuration file, actually, because this is the most important part. At first, we need to we put all the data which are involved in the coupling here, which are force and displacement here. And we also put all the mesh here, and which data would this mesh use? Because if you have multiple coupling surfaces on one participant, maybe this coupling surface want this two data, and another on the other side you want to use another two data, and you need to tell preCICE very accurately about this. And for each participant, we also have some configurations like which mesh are you providing or receiving, and which mapping methods do you want to use, and which data are you reading or writing, and if I think most of the time if these configurations are contradicting each other, preCICE will throw an error. Yes, so the fluid participant will write force and read the displacement, and we want this mapping to be conservative, so we can simply set there. And this is about the communication methods. We use the default sockets communication, and we tell preCICE where is the exchange directory, which means I want to have the directory where they put the temporary files with data in my root folder of this case, actually. Then I configure the coupling scheme. We start with from the serial explicit, and the first participant is fluid. That means we first solve the fluid side. Then we send a velocity. We solve the solid participant. We send the displacement backwards, and then we continue. The maximum time is 1.5. So the maximum time of the coupling simulation is fully controlled by preCICE. It doesn't matter what value you write in your OpenFOAM solver. And we also set the exchange data here, also the direction. Yes, and then we run this case. Keep in mind that we have the solid density 42. It takes about I think 3 minutes to run. Okay, then this is a result of the deformed flap, which is not so rational just from the eyesight, because this mesh has severely deformed. So now we know that there are some unphysical information communicated between the two participants, and now we want to improve. We want to correct this situation by changing our preCICE configuration. And I do another run with a solid density to set to 1, which means a more stronger coupling. And you can see that the solver will break in the first time step because OpenFOAM complains. And what we did so far is a serial explicit scheme. So we have the fluid and send data and solid and send data, and then we move to next time window directly and start again. And we want to try an implicit coupling scheme because, as I mentioned before, through doing multiple iterations for one time window, it can help the whole coupling scheme to converge. Because we think after several iterations, if this time window converges, we can make sure that I have sent some reasonable values to continue the simulation. So we change the setting here. The coupling scheme is serial implicit, and nothing else changed here except that we need to add a criterion to tell preCICE when to stop this time window. That is a convergence measure. We want to use both the displacement and the force as to measure convergence, and if they have reached this relative tolerance, we stop and move to next time window. And you can also use absolute convergence measure or absolute relative convergence measure, and you can read the difference, the explanation to these configurations in the website. And we also set a maximum iterations value here, because sometimes if the time window is not going to converge, we don't want the simulation to run forever. And then with this setting, we run the case again, and with solid density equal to 42, we can see that now the result is quite good. But if I run it again with solid density equal to 1, it will break again, still at the same time. And so we think that it's still not enough only by changing from explicit coupling to implicit coupling if the coupling is very strong. So we have different numerical methods to help the coupling to help the problem to converge. The first basic one is the constant under relaxation. I think you are quite familiar with it because in OpenFOAM you also have it. This will slow down the simulation a bit, but will help it to be more stable. And we choose a random value of 0.5. It could be something else, but with this setting, we can see that we can already solve the problem with solid density equal to 1. And this, because this case is quite easy and simple, you can't see the difference, but sometimes we think it's not enough to only use under relaxation. We can do better if we have more advanced acceleration methods here. So the first choice might be the Atkin under relaxation. The difference is that with these methods, it can automatically choose the under relaxation factor. And the second option would be the EQ family method, which is a quasi-Newton method. For this, you need to tell which data you want to use to calculate the factors inside this method. And you can also have other parameters to which requires quite a bit tuning, but actually it brings a lot of benefit if you. And with the preconditional, we mean that, for example, when we want to communicate a temperature and displacement at the same time, and they are not in the same quantity order at all, because we suppose that temperature is like 200, and I have a 10 to minus 6 displacement, and if we throw these two value arrays into the same method, it's not very rational. So we will scale these quantities to a more balanced order, and then start a method. The filter is very important for implicit coupling, which means that because we redo one iteration a lot of times, and sometimes, and after every iteration, we add one column into the into a matrix inside this method, and sometimes if these columns are linearly dependent, the problem becomes very ill-conditioned, and with filter we can filter these columns. And yes, we also have the maximum, the max use iterations and time windows we used are specifically for ERS. This means that how much historical information you want to use to make the current prediction. And so until here, we have only we're only talking about serial coupling, and we can also use parallel scheme, which means that I start the two participants at the same time, and after that I exchange the information. Oh, there's one thing I forgot to say. That is where we do the acceleration. For serial coupling, we only do this. We only post-process this data when we send the data from the second participant to the first one. But for parallel scheme, we will post-process all the data involved. That is both the data sent from first one to second one, and also in the reverse way. So here you can see how the parallel coupling scheme would be configured. At first is this parallel implicit scheme, and you can see that I can use both displacement and force to calculate to calculate the factors in this method. If it's serial coupling, you can only use force, otherwise it will complain. And here is a table about the average iteration numbers in one time window from different configurations. We can see that this means serial implicit and serial implicit with const under relaxation acceleration. We can see that in both these cases, the serial implicit ERS and parallel implicit ERS has the best performance. And also here, the constant relaxation has already helped a lot by making the case more stable, but it's a little bit slow. But I couldn't see that these two methods are definitely better for your case, because it's purely case dependent. And also the parameters we use in these methods are quite important. this is a graph of the iterations per time window. So the time evolves in this way. And we can see that at the beginning, these methods make quite difference. And after the simulation has reached a steady state, they also somehow converges to a slightly different iteration number. So these results are not from very rigorous comparison. The configuration is not fine-tuned, which means that I didn't choose the best parameters for the under relaxation, also not for the ELS method. So this is only to show how this works. And I paste here some results from the dissertation of Benjamin Uckmann, who is the principal developer of preCICE group. Here is from 3 benchmark cases, and he compared the Atkin and quasi-Newton method using the serial implicit coupling. And we can see that for all these 3 cases, the quasi-Newton methods brings more benefit. And he also compares the serial and parallel coupling by using ELS as an acceleration method. Now we can see that the performance of these methods are quite case dependent. So until now, the technical part is over. I will show you some resources and stories behind preCICE and what kind of also the community itself. First, you definitely want to start from here. This is a website of preCICE, and it has a lot of links to other information. And this is a documentation page, and we have a lot of important topics here listed here. And you can also contribute to this website by clicking here directly and open the pull request. And your contributions are very welcome. And we have a forum. We have a discourse forum for people to discuss programs and also get help from developers or from other users. So this is basically where the people communicate with each other, and is active since October 2019. And we have a lot of posts and a lot of topics here, there. And we have some videos, tutorial videos on YouTube. I am considering to import some videos to some video platforms that Chinese people can reach directly. But if you have suggestions for this, which platform should I go to, please tell me. And we also post some news on Twitter, but I think not quite often since opt is renamed to X, and we are also I think now we have moved to Fostotem. And if you want to read about preCICE or the OpenFOAM adapter in papers, there is a page which is called Cite Us on the website, and you can find papers that preCICE people have published. And this is a one for the adapter, and this is a one for preCICE version 2. And this is a preCICE group, current preCICE group. So Professor Miriam Schulte and Junior Professor Uckmann are the professors here, and we are all PhD students. This is a photo from last year's workshop, and you can see a lot of users, familiar faces here, the developers, and also a lot of users who have a lot of communication with us. And we have an incoming workshop this year, which will happen in Stuttgart in September 24th to 27th. If you want to know more about preCICE, meet the people, meet the developers, and learn more about advanced topics, please register. It's still in the early bird registration phase. And we thank for the funding from this institutes, they are because of their support, we can only because of their support we can have a totally open source software. And so here is a summary. preCICE is both open for developers and for users, and your contributions is definitely encouraged. And many efficient algorithms here are only one setting away, that is for which I mean the configuration file. And you can, this is a QR code to this slide, and if you want to you can find the information of the developers there, and if you want to keep in touch with us, please do it. Thank you for your attention.